Okay, so for part A, it wants us to derive an equation like for momentum, and we know that momentum is mass times velocity, so our derived equation is going to have to involve those. And when I think of like momentum, I think of kinetic energy right away because it has both mass and velocity in it, but according to the system, there's also like a spring, and we have to take that into account, so I'm just gonna use the formula that has like a spring in it, and then we can cancel out our halves because the equations equal to each other. And then we have, I'm gonna change the variables, so md2 is equal to d squared, sorry. And then we're gonna divide by mass. And squared. And that's divided by the equation. So for part B, it's asking to draw the corresponding potential energy. So the first one, the potential energy, which is our first graph. And I'm gonna draw it as a curving upward line because for this we would be looking at 1/2 kx squared, and since we have x right here, that's our d, and if the distance is increasing as the system is moving to the right, so is the potential energy because it's in the equation. And then for the second equation, the second graph, I'm gonna just draw it as a linear, sorry, that's really bad, as a linear, as a positive linear line, because at the beginning, like the spring isn't completely stretched yet. So when it's moving from A to B, the A max is like when it's finally stretched, and that's at point B. So that's why I drew it as an upward positive linear line instead of it going something like downward like that. And then for the for the momentum, it's also going to be like the potential distance graph, because we know that momentum is m times v, and since there's like an increasing a going on in the segment AB, we know that the velocity is increasing, therefore momentum would be increasing since it's in the equation. For part C, it's asking us to derive an equation for acceleration when it's going from C to D. So we know that in C to D we have friction going on, so I'm automatically going to write down f of k. But other things to take into consideration, it's like force is equal to ma, right? So I'm going to have ma, but my force I'm going to change it to the f of k. And then if you break up f of k to fit like using the variables that the FRQ talks about, you have mu k and f of n is equal to ma, but then fn can be broken up into mg. So then you set that equal to ma, which is the same mass because it's the same like the system. And then I'm just gonna rewrite it. So mu k times g is equal to a, because now a is left alone on the other side. And that's the new equation. For part D, it's asking us to derive an equation showing work during the segment of C to D. So we know that work is force times displacement. And then to change two terms of the FRQ, we're going to do work is equal to F of k, because that's the force that is in the segment C to D. And then I'm going to change displacement to D. But f of k is broken up into mg mu k times d. This one be negative. And then that's it. I just changed it to the variables in that FRQ. I'm going to be sketching my graph of the speed. So from point A to point B, I drew it as a linear increasing line because the A max is at point B because that's when the spring is fully stretched. And then from point B to C, our A is 0, so that means that our V is constant, so that's why it's going to be a straight line during that segment. And then from C to D, it's going to decrease because our A is negative, like due to the friction that's going on during the segment. And then after that, I believe that it's just a constant straight line because there's no more A, and so our V is constant.